Welcome to This Explainer. Today, we are unpacking the root causes of common algebraic mistakes and building a toolkit to help you achieve lasting mathematical accuracy. If you've ever felt that sudden giant wall of confusion hit you when looking at a math problem, or if you've watched someone else just completely freeze up, well, you are in exactly the right place. We're looking at how to improve math accuracy, and we're going to do it not just by telling you to practice more, but by fundamentally changing how we actually see and process mathematical information. All right, let's dive right in. Imagine this equation flashes in front of you. 3x plus 7 equals 25. You've got 5 seconds, go. For a lot of us, that ticking clock triggers an instant fight or flight response. When confronted with a sudden equation like this, many students instantly experience cognitive overload and that dreaded math anxiety. The brain literally perceives a wall of incomprehensible letters and symbols, which leads straight to a mental block rather than any kind of logical processing.
Section 1, the Algebra Anxiety Trap.
You see, the leap from simple sequential computation, like basic addition or subtraction, to recognizing abstract structural patterns, that is exactly where so many students get completely stuck. During those crucial ages of roughly 12 to 18, students are suddenly asked to stop just crunching numbers and start manipulating structural patterns. And when they miss this developmental leap, algebra just becomes this set of arbitrary, frustrating rules rather than a beautiful logical system.
Moving on to Section 2, Unmasking Common Math Mistakes. Now, what's genuinely fascinating here is that these aren't just careless slip-ups. They are actually fundamental misunderstandings of algebraic language itself. Take moving terms across the equal sign without changing their sign, for example. That shows a real misunderstanding of what is actually happening mechanically. Or think about misinterpreting the equal sign as merely an operator. Treating it like a prompt that just says, write the answer here, rather than seeing it as a symbol indicating a perfect balance between two sides. And get this, studies show that a shocking 20% of students ignore the presence of variables completely, literally entirely. They'll look at an expression like n plus 5 plus 4 and just solve it as 9, treating the letter n as if it simply doesn't exist. This tells us they aren't just forgetting a rule, they are entirely missing the concept of what a variable actually is. Let's look at a solution in Section 3, Power of Visual Algebra. This brings us to an incredibly effective tool known as the Concrete Pictorial Abstract, or CPA method. It's essentially a cognitive bridge. First, in the concrete phase, you manipulate actual physical objects. Then you draw diagrams. Finally, you transition into traditional symbols. By doing this, it allows the adolescent brain to process math as logical, visual puzzles rather than a terrifying list of arbitrary rules. And honestly, the balanced scale model is just a perfect visual metaphor for this. It brilliantly illustrates the core principle of mathematical equality. Think about it. If you take a weight off one pan of a physical scale, you absolutely have to take the exact same amount of weight off the other side to keep it balanced, right? This ensures students understand the why before they ever try to memorize the rule. Once they grasp this image, they'll never forget the abstract procedure.
Which leads us to Section 4, Unwrapping the Equation.
We so often tell students to just reverse the order of operations to get the variable by itself. But if we shift our language to the gift-wrapping analogy, it completely changes the game. It makes the highly abstract concept of reverse operations super tangible. Think of the variable as the present hidden inside the box. To get to it, you have to undo the packaging from the outside in. You untie the ribbon, you take off the paper, and then you open the box. Now, in math terms, this unwrapping process means using inverse operations. Students really need to understand that taking off that wrapping requires performing the exact opposite operation to whatever was originally done. If a number was added to the variable, you've got to subtract it. If it was multiplied, you divide it. It's literally the mathematical equivalent of untying a knot. To actually put this into practice, we use what's called the peel and solve framework. It gives struggling students a super clear 1, 2, 3 decision-making process. First, identify the outermost operation. Second, apply the inverse operation to both sides. Third, repeat. This tells them exactly where to start. Instead of guessing and panicking, they can just ask themselves, okay, what is the furthest thing from x on this side of the equation? It massively reduces confusion and really builds that accuracy. Let's shift gears a bit. Section 5, Reducing Cognitive Overload. By applying Richard Meyer's cognitive theory of multimedia learning, we can literally design our math materials to completely bypass cognitive overload. Let's break down 3 quick principles.
Signaling uses cues, like little arrows or highlights, to direct attention. Redundancy reminds us not to show massive blocks of text while speaking those exact same words out loud. And coherence means keeping screens clean of irrelevant, flashy animations. We want the brain focused entirely on the learning objective.
Actually, if you look closely at how we've designed this very explainer, you'll see we use strict color coding to anchor the variable and make those operational changes totally unmissable. By always making the variable sky blue, your eye naturally tracks the goal. Using an amber color for operations shows the exact action taking place on both sides of our imaginary balance scale. And fading canceled terms to gray visually confirms, hey, this step was successfully completed.
Finally, Section 6, Building Lasting Math Accuracy.
So here is the absolute ultimate solving strategy to maintain that accuracy. Step 1, rewrite equations into a familiar, recognizable format, something like ax plus b equals c. Step 2, identify what looks physically different from that pattern. And step 3, get rid of it using inverse operations. By consistently rewriting unfamiliar problems into familiar patterns, math stops being this intimidating beast and just becomes a highly predictable system. As they say, you can't make the math harder, you can only make the problem longer.
Ultimately, as this quote perfectly sums up, visual models and structured frameworks replace all that math anxiety with a deep, intuitive understanding. When a student knows the why behind an action, whether it's keeping a scale balanced or unwrapping a gift, they don't have to rely on frail rote memorization. They get to rely on pure logic. So armed with visual algebra, the step-by-step peel and solve method, and these cognitive load strategies, how are you going to transform your math accuracy moving forward? We so often tell ourselves, oh, I'm just bad at math. But what if the problem was never your brain? What if it was simply the way the information was packaged? The next time you see a complex equation, don't panic. Just ask yourself, what is this puzzle actually asking me to unwrap?